So this is an introduction to deductive reasoning. First, let's look briefly at what we're going to go through in this tutorial. To start off, I'm going to give you an example of the kind of deductive reasoning that I think many statisticians are familiar with. Then the next section is about basic concepts in deductive reasoning, after which we're going to move on to talking about different ways in which deduction occurs in science. And then the final slide is going to just summarize this whole content. So the first thing that I wanted to look at is an example of the kind of deductive reasoning that I think that many statisticians have run into, at least during their training, but maybe later as well. So this is a more or less random paragraph from a textbook that looks at the statistical or mathematical foundations of something that's called the classical test theory. And briefly, the classical test theory is a theory that lies in the background of much of measure construction and measure validation in psychometrics. So when researchers validate and construct measures of things like depression or personality, then classical test theory is often in the background there. So what matters here is not so much the content of the paragraph, but more the form that the argument takes. So in the first part, the authors lay out some assumptions. So they say, now let us assume that. And then they talk about relationships between certain variables. Here the variables are observed scores, expected or true scores, and the error variable. So that's one part of the assumption. And then the other part of the assumption is the variances of the error variables. So that's the first part, and that's the assumption part. And then in the second part, the authors go on and derive some consequences with these assumptions. So they say two immediate implications of this assumption are that. And then they say that the consequences have to do with the means of the observed scores and the variances of the observed scores. Now, so this is an example of a deductive argument, and we can interpret this two immediate implications as the claim that the authors don't need to look at the world, they don't need to run experiments, they don't need to do a lit review to arrive at these conclusions, but rather the only things they need are the assumptions that they have laid out, some earlier definitions perhaps, and then the rules of logic. And then the consequences follow from that. So this is one way in which deductive reasoning might manifest in statistics or other scientific fields. From now on, I'm going to be using verbal examples rather than these kinds of numerical and formal examples. And the reason why I'm going to be using verbal examples is that I think that they might be a little bit easier to follow. And also with verbal examples, we can sort of zoom in on other aspects of deductive reasoning in science, not just the formal foundations of a given science. Now, let's move on to looking at some basic concepts in deductive reasoning. So take a look at this argument. The first premise is that all humans are mortal. Then the second premise is that Malla is human. And the conclusion is, therefore, Malla is mortal. So this is a deductively valid argument, but what makes it a deductive argument? You might have seen deductive arguments characterized as arguments that start from the general and infer to the particular. That characterization does fit this, this example, but I think that perhaps a more useful or more exact characterization of a deductive argument is this. In a deductive argument, if the premises are true, then the truth of the conclusion follows by virtue of the rules of logic. So for instance here, If we have the assumption or the reason to believe that the premises are true, we don't need to gather evidence, run experiments, or anything like that. We simply consult the rules of logic, and the truth of the conclusion follows from there. Now, it's important to know this, though, that we need to have reason to assume that the premises are true in order for us to have reason to believe the truth of the conclusion as well. So let's take a look at this argument then. Here, premise 1 is all sad people have depression. Premise 2 is that Tove is sad. And then the conclusion is that therefore Tove has depression. Now, this argument is deductively valid, but it is not sound. So as you can see, premise 1 is quite clearly false. It is not the case that all sad people have depression. And that's why we should not have faith in the truth of the conclusion either. So a valid argument is one where if the premises are true, then the truth of the conclusion follows by virtue of the rules of logic, whereas a sound argument is one where the premises are true and then the truth of the conclusion follows. So that's an important distinction to keep in mind. Not all valid arguments are sound. Now, the next thing that I wanted to talk about is some examples of deductive reasoning in science, or at least examples of the kinds of things famous thinkers have said about the applications of deductive reasoning in science. One of the methods that we should look at here is the hypothetical deductive method. And as the name suggests, it has something to do with deduction. So in a hypothetical deductive method or model, the researchers start off by looking at some background information, perhaps earlier experimental results, and they formulate a theory on the basis of that, that material. So for example, we might have a theory of water or the properties of water, and it's a big theory. It has several aspects to it, but let's say that one part of that theory says that all water is tasteless under certain circumstances, for example, in room temperature. So our big theory about the properties of water states that all water is tasteless. Then the next step in the hypothetical deductivist method is deriving consequences of this theory. So the idea is that we try to figure out what kinds of experimental results would have to occur if our theory were true. So if our theory of the properties of water is true, what would have to happen in an experimental setup? And one thing that we might say or expect or predict that would happen is that if our theory about water is true, then in a study where we have samples of water under certain circumstances, for example, in room temperature, those water samples would be tasteless. Then in the third step, we conduct the study that tries to either falsify or confirm our predictions. So here, for example, let's say that we taste some samples of water and it turns out that, that these water samples were all tasteless in the circumstances that we have laid out. So does this then allow us to conclude that our theory of water is true, in particular that all water is tasteless? Well, it turns out that it does not allow us to make this conclusion, at least not on the basis of deductive reasoning. So if from the confirmation of the prediction, we would deduce the truth of the theory, we would be committing a fallacy. And this fallacy is known as the fallacy of affirming the consequent. Now, why would this be a fallacy? To convince you of the fact that this is a fallacy, you can take a look at the truth table of if-then statements. This is one way in which you can present the truth table of an if-then statement. And so here you should look at the part of the table that I have squared with a red line. And you will notice there that just from looking at the truth of the prediction, which is the latter part of the if-then statement, you cannot infer, or you cannot say anything about the truth of the theory. So the whole if-then statement is going to be true whether or not the first part, which in this case is the theory part, is true or false. So what we should conclude from this is that there are some serious obstacles to deductively confirming a theory. And the biggest obstacle is this fallacy of affirming the consequent. Instead, we say that the confirmation of our prediction, it corroborates our theory, or it supports evidence in favor of our theory, even though it does not confirm it by means of a deductive logic. So we have said that confirmation runs into trouble when it comes to deductive mode of reasoning, but what about falsification? Let's take a look at a different theory. Let's say again that we have a big theory about water, or H2O. And one part of that theory says that all H2O is liquid. Then again, following the hypothetical deductivist model, we make some predictions on the basis of this theory. So for example, our prediction could be that then a sample of H2O is going to be liquid in our study, or all samples are going to be liquid if our theory is true. So then we run some studies, and it turns out that, well, not all H2O was liquid in our study. So for example, let's say that we have specified the conditions of the study so that some of the samples were ice, and that's why not all samples were liquid. So we have falsified our prediction, it looks like. Can we now conclude that our theory is false as well? Well, in principle, we can. So it's a deductively valid argument to then conclude from this that therefore it's not the case that all H2O is liquid. And this argument form is called the modus tollens. And to summarize this argument form, it's one where from the falsity or falsification of the latter part of the if-then statement, which in this case concerns the prediction, so the falsification of the prediction allows us to make the deduction that the former part of the if-then statement is also false. In this case, the former part is the theory. So falsification is in principle possible by means of deductive reasoning. But why did I say that falsification is in principle possible by means of deductive reasoning? Well, let's take a look at this argument then. So let's say that we have a big theory again about different aspects of depression. And let's say that one part of that theory talks about the relationship, perhaps a causal relationship between depression and social isolation. And then from this theory, we make the prediction that isolation is associated with depression in empirical study S, which is conducted under certain circumstances. So we have a theory and we have a prediction. Then it turns out that when we run this empirical study, that isolation was not associated with depression. Should we then reject our theory of depression on the basis of which we have made this prediction? Well, it would seem like there are a number of reasonable things that we can do that are not the rejection of the theory, even though we have, it looks like we have falsified the prediction. And for example, what we might want to say is that we want to specify the conditions under which the relationship between depression and isolation manifests. We want to be clearer about the context in which this association would be expected. Another thing that we might want to say is that there's something wrong with the empirical study. So it could be that perhaps we used a bad measure of depression in this study, or perhaps we used wrong way of categorizing people as depressed or not depressed, or isolated and not isolated. So the idea is that there are various things that we might do by way of tweaking the study or the theory that look like reasonable things to do, rather than reject the theory altogether. And so the general point here is that it's hard to tell what part of the theory we have falsified when we have falsified a prediction. And moreover, it might not be an explicit part of the theory that we have falsified, but rather it might be some kind of background assumption that perhaps we're not even very aware of when we have formulated our theory or formulated the predictions. So the general point here is that there are some problems to deductively falsifying a theory in practice. Okay, so the final thing I want to talk about is a summary of different important aspects of deductive reasoning. So here's a little checklist of things that I think are worth considering when it comes to deductive reasoning and statistics. So first of all, it's important to be aware of the important role or the crucial role of deductive reasoning in the mathematical foundations of statistics. And moreover, if you have studied the mathematical foundations of statistics, which I think most statisticians have during their training, then you have already some familiarity of one form of deductive reasoning. The second thing that's important to remember is the distinction between a valid and a sound argument. So a valid argument is one where if the premises are true, then the truth of the conclusion follows. Whereas a sound argument is one where the premises are true, and then the truth of the conclusions follows by means of deductive reasoning. Then when it comes to deductive reasoning in science, we looked at confirmation, and we observed that there are some serious obstacles to deductively confirming a theory. And the most well-known obstacle to confirmation is called the fallacy of affirming the consequent. So confirmation has some problems, but falsification is in principle possible by means of deductive reasoning. And the argument form that falsification takes is called modus tollens. So if you want to know more about falsification, then you should look at modus tollens, among other things. And then finally, even though falsification looks very neat in theory, there are some practical limitations or practical problems with falsifying a theory when we are conducting experiments and formulating real theories in real life. So yeah, that's the full extent of this tutorial. I hope you enjoyed it.
Hey guys, it's Glenn. Thanks so much for listening to this most recent episode of the Philosophy of Data Science. I hope you enjoyed it. If you did, please consider leaving a like, a comment, and hitting that subscribe and bell button. We're a small channel and every bit helps. If you have a lab, a department, some students, or some colleagues who you think would enjoy this episode, please consider sending along. Again, every bit helps, and we really appreciate your word of mouth. Our next episode on the Philosophy of Data Science will be coming out 1 p.m. Eastern Time, Wednesday of next week, so we look forward to seeing you then. But if you can't wait to get more data science, machine learning, and statistical content, feel free to look around the rest of the channel. We have a large number of playlists, including things like machine learning for healthcare, ethics and AI, and things like that. So give a look around. There's plenty more content for you to enjoy. You can also check out our website to not only see past episodes, but what's coming up, and see who our sponsors are. Thank you to our sponsors for your support. Now, while the views discussed on the show typically range between extraordinary and mind-blowing, the stated views don't necessarily represent those of the host, our sponsors, my employer, your employer, the speaker's employer, or anyone else not saying those words. And as always, thank you so much for your time. I really appreciate it. See you next week.